In this video, we will be doing some questions from homework 2. We're going to do the Kung Fu Panda scenario, and then we're going to do the Ford event t-shirt scenario, inventory management questions. So for this question, we're given some data, and we have data on demand, and we have data on lead time. Okay, so you can see that demand is changing day by day. It's not constant. Lead time is changing day by day. So immediately we know it is the scenario in which demand is variable and lead time is variable. Next thing we notice is that inventory levels are checked once a week. So it is not continuous review, it's a periodic review inventory system. Okay. First thing we have to find statistics on demand and lead time. So we can use the average function of all of the data points to find the average demand. Then we can use the standard deviation SDDEV.S. This is a sample of data on the same values, and we get the standard deviation of demand. So this is called SD or sigma D in the formulas, and this is called small d, it's demand per day. It's not annual demand. Big D is annual demand in formulas. We do same thing for the lead time. We use the equals average function in Excel, select all these values, which are actually less than the values here. Now, if you do select empty cells in Excel, it does not affect your statistics. But if there's a 0 here, it will affect your statistics. So empty cell means not 0, nothing in it. So empty cells do not affect the average of the standard deviation, but we can just exclude them anyway. Just select the data, and that should be our average lead time. Similarly, we can find the standard deviation of the lead time for the 20 orders that we are given the data for, and there is a standard deviation, a non-zero standard deviation of lead time, which is called sigma L or SL in the formulas. We can see from the slides that when you have variable demand, variable lead time, the standard deviation sigma P plus L that we need for the safety stock calculation for a periodic review system, which is what we have here, is given by this long formula. So you do P plus the average L times sigma D squared, which is SD that we written in Excel, because sigma is kind of hard to write. You have to insert symbol in Excel. So I just replace sigma by S when I write it out. And then we have a D squared, and then you have the lead time sigma L or SL squared. It says LT here, you can call it L or LT. That's the lead time standard deviation squared. So if we go to our Excel sheet, we have to find that the sigma of P plus L, okay, and to do that we do a square root, okay. We know that this whole thing is under a square root. Then you do P plus L. So we have not written out P plus L first. So let's do that first. Well, we have L here. We need P. P, I believe, is 7 days. Once in 7 days, inventory is checked. Okay, and we can just double check with the question. Once a week to check inventory levels. So every 7 days inventory is checked. So that is P. Okay. So we do square root of P plus L times standard deviation of demand squared plus, let's check the slides again to get it exactly right, the average demand squared and standard deviation of lead time squared. So then we'll take the demand squared times the standard deviation of lead time squared, and that gives us S sigma P plus L, standard deviation of demand over the P plus L interval. Once we have that, we multiply that by Z to get the safety stock. So Z we need based on the cycle service level, which is 98%. So we do equal norm.s.inv 0.98, convert probability to a z-score. Norm.s.dist will take a z-score, convert to a probability, and norm.s.inv is the reverse, give it a probability like 0.98, will give you a z-score. So So that's 2.055. So then we have safety stock is simply the z-score times sigma p plus L, which is right here. Okay, we're going to need the average inventory level as well. So if we go to this slide, slide number 26, we have average inventory level is given to, this is just safety stock, just calculated that. So we have average demand times P over 2 plus the safety stock. Okay, so we take the average demand times P divided by 2 and add to that the safety stock, and that's our average inventory level. Okay, so we have to calculate a T as well, and the annual holding cost. Okay, to calculate annual holding cost, that's really easy once you have AIL. We need some other parameters. We need the holding cost H, which is 25%. We need the cost of each item, which is $2. So this is all given in the question. Box of noodles costs $2. That's C, the cost of an item. And holding cost is 25% of the item's value, so it's 25% of that. So annual holding cost will just be H times C. H times C gives you the annual holding cost of one box of noodles. But how many boxes of noodles are you actually holding? Well, you're actually holding average inventory level box of noodles. So we multiply by that, and that's our average annual inventory holding cost in dollars per year. We need to find the target level T. We can go quickly back to our formulas to find T. So T is equal to average demand times P plus L plus safety stock. So that's really easy. We take the average demand times P plus the lead time, just plugging and chugging the formula. That's D times P plus L. So D right here times P plus L plus the safety stock. So once you get safety stock, things become easy, right? So that's your T. Okay. So that's pretty much it for the Kung Fu Panda scenario. We're going to do the periodic review system, safety stock we calculated, target level T we calculated, average inventory level AIL we calculated, annual holding cost we calculated. Last question, if you're holding 2570 boxes in inventory, you have placed an order for 3000 boxes. So inventory at hand, 2570, inventory in pipeline, i.e. orders placed, 3000. That means my inventory position is going to be inventory on hand plus inventory that's already been ordered, that's on the way. That's my inventory position. And how much will I order? You'll order to take inventory position up to T. So the difference between T and the inventory position is how much to order. So order quantity will just be this number T, the target level, minus the inventory position. That's 1462.5 or 1463 to the nearest integer. Okay. And now that's it for the scenario. Now we do the Ford scenario. So we're selling some toy versions of a car. We have a demand distribution given here. And what's the optimal quantity to keep in stock? So I took the liberty of entering the question data here. So this is the probability distribution. I know I'm going to need cumulative probabilities. So what I did is I know that the probability of 100, okay, is 0.05. So what is the probability I'm going to be less than or equal to 100? That's simply 0.05. Okay. Okay. What is the probability I'm going to be less than or equal to 200? Well, that's the probability I can be 200 or lower. So that's these two probabilities added together. So if you add those two probabilities, you get 0.11 plus 0.05 or 0.16. Similarly, you can just drag the formula down. 0.34 plus 0.16 gives you 0.5. The probability you're going to be 300 or less in demand. Demand can be 300 or less is equal to 0.5. That's a cumulative probability, and it goes up all the way to 1. Now, to do any of this analysis, you need to find cost of excess and cost of shortage. So C is cost of excess, CS is cost of shortage. So think about it this way. If you have one extra t-shirt left at the end of the day, what is the cost of that? Well, you paid $40 for the t-shirt at the start of the day to bring it to, not the t-shirt, just the toy car. So you paid $40 for the toy car whatever item we are selling. What are we selling? Toy, Ford Mustang toy cars, right? So it costs us $40 to buy the toy car from the supplier, and at the end of the day, when we have this one extra toy car left, when we return it to the supplier, he'll charge us a restocking fee and only pay us back $30. So we lost $10 by having this extra car. So my cost of excess per unit, this is per each extra car, is $10. Now, cost of shortage, if I have one less car than I needed, well, if you had one less car than you need, then you sold one less car. So what is the loss of not selling a car? You sell for 75, you buy for 40, you make $35 profit on a car. You lost that profit because you didn't have that one car in stock. So the cost of a shortage is $35. So our critical ratio is CS, cost of shortage, divided by CS plus CE. So we do that, and our critical ratio is 0.777 or 0.778. And so we have to find the cumulative probability, which is 0.778, and read off the quantity here. Now there's no 0.778 here, so we go to the closest next highest probability. We don't round it down because we don't want, because usually the cost of shortage is higher than cost of excess. And so we lean towards having too much rather than too few. So if you lean towards having too much rather than too few, then you're going to round the ratio up, right? So usually, as a rule of thumb in this course, you can just round the ratio up. Although it, in some weird scenarios where cost of shortage is too small and cost of excess is a lot, it may make sense to round the ratio down in the cumulative probability table. But you're always going to round it up because we're going to go with a normal scenario where cost of shortage exceeds cost of excess. So in the normal scenario where cost of shortage is bigger than cost of excess, we round, and for this course, that's what we're going to assume. We round this up to the next highest value. So it's going to round up to 0.84 because there's no 0.778. It's between 0.5 and 0.84. So if you round to 0.84, you get quantity of 400. So we will order 400 toy Ford Mustangs and take the 400 to our stand to sell. Now, the second part of the same problem is that we have exactly the same setup, except this is not our demand distribution. We have kind of estimated that our demand is going to have a normal distribution with a mean of 350, standard deviation of 100. So we're going to still use the same ratio because cost of excess, cost of shortage has not changed. And so our ratio has not changed, right? And so it's going to be the same ratio. Okay, but our demand distribution has changed, so we put that ratio not in this table but somewhere else. So that's going to be our z-score, and then we're going to use this. So we're going to do norm.inv, okay, our ratio, and then our mean is going to be 350, standard deviation is going to be 100. So that's 426.47. And let's check the rounding rules in the question. Round to two decimal places, so we'll just enter 426.47. Another way to do the same thing is that you use norm.s.inv. That S means it's standard, so you just give it the z-score. It doesn't need mean or standard deviation. It just needs a probability. So it uses a probability, which is 0.778. It converts the probability to a z-score of 0.7647. And then you can convert the z-score by multiplying the z-score by the standard deviation and adding in the mean, and you get to the same answer that you got with norm.inv. So norm.inv is the one-step way to get it, or if you want to first convert the probability to a z-score, you can do that with norm.s.inv and then convert the z-score using these back to the actual scale of the quantity we are concerned with. So that is it for this fourth scenario as well, and that ends this video. Hope it was helpful. If I went too fast, you can probably this controls to slow down or speed up the video. You can pause, you can slow down, you can rewatch. Do this in your own Excel so you get